Alright, this video is on friction, so let's get started. A couple things about friction that we should know is one is that frictional forces act on objects to oppose their motion. So if we have a block that we're sliding across the table, friction is there to slow it down. Also, air resistance or air drag is a frictional force that opposes motion in planes and cars and when you're running, etc. Friction, though, isn't always bad. We need friction to actually get us to move. So it also helps put objects into motion. So if there was no friction between a car and the tires, or the car tires and the road, then the car would just spin out. So the wheels, the tires would spin, and there would be no traction, no friction, so there would be no push back from the road on the car. And therefore no motion. So it's not always a bad thing, but when we're moving, we typically want to reduce friction so that we can move with less force. So how do we calculate forces of friction on objects that are sliding? So a couple things. It depends on two factors. The first one is the surfaces that are in contact. So it depends on the type of materials that are in contact. So you are going to have different frictional forces between, let's say, your sock and a tile floor and your shoe in a tile floor. So if you think about it, a sock on a tile floor doesn't provide a lot of friction. You can slide, whereas a shoe provides a lot more. And we don't change anything about it. You're still the same person. You still have the same mass and the same weight. The difference there is the materials that are in contact. And B, the other thing is what's called the normal force. Now the normal force is a force that is acting perpendicular to the surfaces that are in contact. So if you place a book on a table, the book is applying a force on the table which is equal to its weight, and the table is applying a force to the book to support it so it doesn't accelerate downward. And that force, which is a support force, we call the normal force. So let's look. We have a block, we know its mass, we want to find the normal force. Well, let's look at the forces acting on the block. We have a force downward, which we've called the weight, and we also have a force upward, which we're now calling the normal force. Again, it's perpendicular to the surface right here. And because this block is not accelerating, it has a net force of 0, so that means that the forces down are equal to the forces up. So therefore, the normal force is equal to the weight, and we can show it by this equation here. Now let's say that that block is now being pressed on. So a different block, I guess, is 45 kilograms, but now we're pushing down on the block with 200 newtons of force. So let's look at the forces. We have the weight. We also have a force pushing down on it of 200 newtons. So now let's think. If we're a support force, if we're the floor pushing back, how much force am I going to need to supply? Good. I need the weight plus 200 newtons. So it's the sum of those. So the normal force is now increased. Imagine that you put a spring scale, like a bathroom scale, underneath this. And you have a block that you sit on it, and then you push down on the block on the top. What's the spring scale read? It reads what you push plus the weight. And that's what the support force is telling us here. So here's our blank equation. A little substitution here for weight. And then we have to show an addition rule here because of this. This is our multiplication rule. So 3 digits, answer is going to have 3 digits. Carry some extra digits and underline it, and then we look at place values. This is good to the ones, so my answer is good to the ones. I can circle my final answer. Two types of friction that we're going to look at. One is called static friction, which is the minimum amount of force required to overcome or to initiate an object's motion. So the object is sitting there. So imagine your book, if you have a book at home, and put an object on the book and start raising one end of the book up so you're making an incline out of it. Well, that object might not start rolling right away, especially if it's a flat object. It's going to stay put. But if you keep raising the book up, raising the incline, eventually it'll start to slide. And now there's enough force due to the weight of the object that's now pulling down on it, causing it to slide. And that would be the static friction, the force to get it to start to move. The other type of force that we have is our friction is called kinetic friction. So kinetic friction is, again, the frictional force that's acting on an object when it's in motion. And a couple things. The values of static friction are always going to be greater than the kinetic friction, because once an object is set into motion, it's now easier to keep it moving based on the law of inertia. It says when you wish to push your couch across the level 4, you must first overcome the force of static friction to get the couch moving. Then you must apply a force equal to the kinetic friction to keep the couch in motion at a constant speed. So how do we calculate static friction? It's really pretty simple. This right here is the Greek symbol mu, and mu sub s is the coefficient of static friction. So this is it's a coefficient, so it's unitless, and it's dependent on the materials that are in contact with each other. So these are values that you can look up in tables to find, or you can solve for them based on some experimentation, which we'll be doing later in one of our inclined plane labs that we do. The larger the coefficient of static friction, the larger the frictional force, and a small value for that means small frictional force. Fn, we've already talked about, is the normal force. So let's look at a problem. Here we have a sled. It's resting on snow. It's horizontal. We know the coefficient of static friction, and we know the mass of the sled, and it has a boy with that mass sitting on it. So we have to overcome static friction. We want to know what force is required. So if it's not accelerating, then these forces are equal to each other. So what's the amount of static friction that's this has to overcome? Well, we have the weight of the sled. We also have the weight of the boy. And then the normal force is those two added together. So we first solve for the normal force. And now we can plug it in, and we know the coefficient of static friction, which is given up above here. And plug it in with the normal force to find the amount of friction that needs to be overcome. So we need to apply a force of 240 newtons to overcome the static friction force to get this sled moving. And again, if we had a bigger boy, if he was heavier or a more massive sled, then it would take more force. And if we had different materials, then it could take more or less force depending on the coefficient of static friction. We have another problem. We're going to look at kinetic friction. It's very similar. It's found the same way as static friction. We have just a different coefficient. So this value is different, and it's smaller than the coefficient of static friction for two surfaces. So let's look at this problem. Very similar. We still have a sled. We have a girl now sitting on the sled, and she's moving with a constant velocity. We want to know what force is required to keep her moving at a constant velocity. So in order for that to happen, the net force is 0. That means the force that's in the direction of motion is equal to the forces that oppose motion. So therefore, the force that we're pushing with is equal to the force of kinetic friction. So we can show those two vectors that are acting on the sled. And what else do we know about it? Well, we know that we have the weight of the sled and the girl, and then we also have the normal force that's balancing that. Since she's not accelerating vertically, those are equal to each other. We can solve for the normal force. We can use that value then to solve for the kinetic friction. So to keep the sled moving at a constant velocity, we would have to be applying a force of 27 newtons to do that. And that's it. Have a great day.